Hello, and welcome to our video on line integrals. Let's fix a function f defined on a set D contained in the complex plane that is continuous, and let's fix a curve defined on the set AB contained in the reals into D. Now this is just to say that the image of this curve gamma lies in our set D in the complex plane, and the domain of gamma is the real interval a to b. We define the line integral of f over gamma to be the following expression. The integral over gamma of f is the integral from a to b of f of gamma of t times gamma prime of t. This is when gamma is a curve that is continuously differentiable on all of the interval a to b. So on the left, we just have a symbol, the integral over gamma of f of z dz. On the right, we have an integral over the real interval a to b of a function f composed with gamma of t times gamma prime of t, where here t is a real variable, and the integrand f composed with gamma times gamma prime is a complex valued function. So on the right, we just have an ordinary Riemann integral, if you like, as we've used a lot of times throughout the course, going from the reals into the complex plane. On the left now, we have a symbol for the integral of a function defined on a subset of the complex plane. Now, if gamma is a curve that is continuous but only piecewise continuously differentiable, we can partition the interval a to b as a equals t0, and then we'll have a point bigger than t0, call that t1, all the way up through a point tn, which is equal to b. And we know that gamma will be continuously differentiable on the open intervals tk minus 1 to tk. And so we'll define the integral over gamma of f now to be the sum of these n integrals from tk minus 1 to tk of f of gamma of t times gamma prime of t. Now let's say we take a number z0 in the complex plane and a real number r greater than 0. We talk about the circle modulus of z minus z0 equals r. This is the boundary of the ball centered at z0 of radius r. And we choose in this course always to interpret this circle as being parametrized by the function gamma of t equals z0 plus r e to the it for t between 0 and 2 pi. And so we will define the symbol integral over the curve modulus of z minus z0 equals r of f. This symbol for us means the integral from 0 to 2 pi of f of z0 plus r e to the it times ri e to the it, or if you prefer, ir times the integral from 0 to 2 pi of f of z0 plus r e to the it times e to the it. We will integrate over circles very, very often in our treatment of complex analysis, and when we do, we're always assuming that the circle is parametrized in this, shall I say, counterclockwise manner. Let's actually calculate an integral. So again, we'll fix a point z0 in the complex plane, a real number r greater than 0, and an integer n. And we want to calculate the integral over the circle modulus of z minus z0 equals r of the power z minus z0 raised to the n. This is an integral that will show up many times in different calculations and proofs. So, when all else fails, go to the definition. The integral over the modulus of z minus z0 equals r of z minus z0 raised to the power n, by definition, that is I times r integral from 0 to 2 pi of z0 plus r e to the it minus z0 raised to the n times e to the it. So that simplifies a little to I times r times the integral from 0 to 2 pi of r e to the it raised to the n times e to the it. That's ir times the integral from 0 to 2 pi of r to the n times e to the int e to the it. Remember that when we're dealing with complex exponentials and integer powers, we can move the powers into the exponent just as we can with real variable stuff. And this simplifies to I times r to the n plus 1 times the integral from 0 to 2 pi of e to the I n plus 1 times t. Now this very last integral is an ordinary Riemann integral of a continuous function, we can use the fundamental theorem of calculus just as we've been doing for years here. So first, if n plus 1 is not 0, then the antiderivative of e to the I n plus 1 times t is e to the I n plus 1 times t over n plus 1. So the integral from 0 to 2 pi of e to the I n plus 1 times t is just going to be e to the I n plus 1 times 2 pi over n plus 1 minus 1 over n plus 1. And of course, that is 0 because e to the I n plus 1 times 2 pi is equal to 1. Now the important thing here is we specified n plus 1 was non-zero, so we could divide by n plus 1 to get this antiderivative in the first place. If n plus 1 equals 0, however, then our integral is just the integral of 1 with respect to t, which is just t. And so the integral from 0 to 2 pi of e to the I n plus 1 times t when n plus 1 equals 0 is just 2 pi. So we have two cases governing our solution here. When n plus 1 is not 0, which is to say when n is not equal to minus 1, and when n plus 1 equals 0, which is to say when n equals minus 1. And we conclude that the integral over the curve modulus of z minus z0 equals r of z minus z0 raised to the power n is equal to 0 for n not equal to minus 1 and 2 pi I from for n equals 1, going back to our formula on the previous slide. And we will use this value of this very special integral quite a lot throughout the course, so it is worthwhile committing to memory. Last, let's give a few fundamental properties of line integrals, and I'll assume that the functions and curves are nice enough in the following statements that all the integrals are defined. First, the integral over a composition is the sum of the relevant integrals. That is, the integral over gamma 1 composed with gamma 2 of f is the integral over gamma 1 of f plus the integral over gamma 2 of f. Second, the integral over the reverse is negative of the integral over the original curve. That is, the integral over gamma reverse of f is minus integral over gamma of f. And these two properties, I think and I hope, make a lot of intuitive sense. You can integrate over the whole curve gamma 1 composed with gamma 2, or you can do gamma 1 and then add that to the integral over gamma 2. And if you're going backwards along the curve gamma, that's the same as negative times going forwards along the curve gamma. And also we have a fundamental theorem of calculus for line integrals. So let's say that big F prime of z is equal to little f, and say we have a curve gamma with initial point z1 and terminal point z2. Then the integral over gamma of little f is big F of z2 minus big F of z1. So just as with the fundamental theorem of calculus for real Riemann integrals, if you know an antiderivative and you know the initial and terminal points, then you know what the whole integral is. You don't have to worry about using the definition. Let's prove this fundamental theorem for line integrals. I'll assume that my curve gamma is continuously differentiable over the whole interval a to b, which means that the integral over gamma of little f is going to be, by definition, the integral from a to b of f composed with gamma of t times gamma prime of t. If gamma were not continuously differentiable over the interval, but just continuous and piecewise continuously differentiable, then you'd have to break this integral up into a sum, and that is available for you to read in the notes. So let's look at the second integral from a to b of f composed with gamma times gamma prime. I'm going to replace little f with big F prime. So this is the integral from a to b of big F prime of gamma of t times gamma prime of t. Look at that integrand for a moment and recognize it as the chain rule. So this is the integral from a to b of the t derivative on f composed with gamma. So I have the integral of a perfect derivative. This gives me f of gamma of b minus f of gamma of a. And what is gamma of b or gamma of a? Well, it's just the initial and terminal points of the curve. This is f of z2 minus f of z1. This is our fundamental theorem of calculus for line integrals.